Good morning. We are going to see about the transmissions at high frequencies. Before we are going to see the transmissions at high frequency, or we can call it as a radio frequencies, there are some assumptions we have to make. So when a line either open wire or a coaxial type is used at radio frequencies, the following assumptions are made. So before we are going to see about the assumption, first we have to know what is skin effect. So skin effect. The flow of alternating current on the surface of the conductors is called as the skin effect. The skin effect will affect the conductor's size. So only it happens at the high frequencies. So these are all the assumptions you have to make at the high frequencies. This first one, the current is considered as flowing on the surface of the conductor in a skin of very small length. That is, it is not going to be affected. Second one, that L omega should be very greater than R because of this skin effect, that we can call it as R is very smaller. And next, G may be considered as 0, that is radiation losses in your open wire become appreciable for high frequencies, that is only about 300 megahertz, but in a coaxial cables can handle frequencies up to 8 gigahertz. So for open wire frequencies, the skin effect is considerably high. For coaxial cable at high frequencies, because of skin effect, the current flows on the surface of the inner conductor and the inner surface of the outer conductor. The internal flux and internal inductance are reduced nearly to 0. So the capacitance of the coaxial cable will not be affected at high frequencies. So what are the parameters we are going to see on the open wire line and coaxial cable? First we are going to see about open wire. Open wire, we can call it as a parallel wire, or we can say that two-wire system. So at high frequency, the current is flowing on the surface of the conductor in a skin of small depth. So the internal flux and internal inductance will be reduced to 0 here. So what is the value of L here? What are the parameters we are going to see about here is inductance and capacitance. So L is equal to mu naught by 2 pi ln D by A Henry per meter. That is where A is the radius of the open wire line and D is the distance between the two open wire lines. So what is the value of mu? Mu naught. Mu is equal to mu naught into mu R. Mu R value, reliable permeability value, will be equal to 1, or it depends upon the material we have used. Mu naught is having a constant value, that is mu naught value is 4 pi into 10 to the power of minus 7. So next we are going to see about that value of capacitance. The value of capacitance of an open wire line is not affected by skin effect at high frequencies. So C is equal to pi epsilon naught by ln D by A farad per meter, where epsilon is equal to epsilon naught into epsilon R. It is permittivity. So epsilon naught is a constant value. Its value is 8.854 into 10 to the power of minus 12 farad per meter. If the current flows at high frequencies over the surface of the conductor in a layer, there will be a increase in resistance also. So that the skin effect or effective thickness of the surface layer of the current is given by 1 by root of pi f mu sigma. For direct current resistance of the open wire is given by RDC is equal to K by pi A squared. We know the value of R depends upon road length by area, that is length of the wire and by area of a wire. So for alternating current, the resistance of the open wire is RAC is equal to K by 2 pi A sigma. So RAC is K divided by, we have seen that skin depth value, so we have to substitute the skin depth value here. So we get the RAC value as K by 2 by A root of mu sigma by pi root of F ohms per meter. So this shows that the resistance increases with the increase in frequencies. Next we are going to see about the parameters inductance and capacitance in the coaxial cable. So the parameters of the coaxial cable are also modified by the presence of the frequency currents on the line. So because of skin effect, the current flows only on the surface of the conductors, and so it eliminates the flux linkages. The inductance of the capacitance of the coaxial cable is given by L is equal to mu naught by 2 pi ln B by A, where B is the inner radius of the outer conductor and A is the outer radius of the inner conductor. The capacitance of the coaxial cable is not affected at high frequencies. So there is an increase in the resistance of the conductor. The skin depth or the effective thickness of the layer of the current is given by sigma is equal to 1 by root of pi f4 sigma. That is the value of RDC in coaxial cable, K by 2 pi sigma into 1 by A plus 1 by B. So the resistance increases with the increase of the frequency values. So next we are going to see about what are all the line constants for the zero dissipation. The line constant for transmission line, zero dissipation. What is meant by zero dissipation? We can call it as a dissipation less line also, that is lossless line. So we have to get the transmission from sending end to receiving end without any losses, that we can call it as a zero dissipation. So what are all the line constants for transmission line? We are going to see about as Z is equal to R plus J omega L, Y is equal to G plus J omega C. As we know, the characteristic impedance Z0 is equal to root of Z by Y. So it has substitute and you can get the value for Z0. Propagation constant is equal to root of Z into Y. That is, we can call it as a alpha plus J beta also. So where R is resistance per unit length and L is an inductance per unit length and C is the shunt capacitance per unit length and G is the shunt conductance per unit length. As we have seen already, what are the assumptions we have made? So according to the assumption, we can say that for zero dissipation, R is considered as very low when compared to the reactance, and also the G is assumed as 0. So the value of Z is equal to, when you substitute that, Z is equal to, we know that value is R plus J omega L. Since R is very small, we can consider that it is a 0. So anything is added by R plus J omega L. Since R is smaller than omega L, we add to those values, we can get the J omega L. Similarly, Y is equal to G plus J omega C, and the assumption we made, G is considered to be as 0. So here the value of Y becomes J omega C. So what will be your value of Z0? So root of L by C. So next we can see the propagation constant. We can see that alpha plus J beta. So that is root of Z by Y. So if you substitute that, we can get the value of propagation constant as J omega into root of LC. So we have equate that to an alpha plus J beta, as we have already seen that propagation constant is equal to alpha plus J beta value. So if you equate that real part to real part and imaginary part to imaginary part, since there is no real part, we can say that alpha is equal to 0 and beta is equal to omega into root of LC. So what are all the line constants for zero dissipation? We can say that attenuation will become 0 and your beta value will become omega into root of LC. So ultimately we can say that the propagation constant gamma is equal to omega into root LC, or gamma is equal to J beta. So similarly, we are going to derive the values for voltages and current values on the dissipation less line. So as we have going to consider that the length of the line is equal to X. So what will be the value of your voltage and current for the dissipation less line? as we have already derived that equation, V is equal to VR into ZR plus Z naught by 2 ZR into e power gamma x plus ZR minus Z naught by ZR plus Z naught e power minus gamma x. So what is VR? That we can call it as a receiving end voltage. ZR receiving end impedance. Z naught we know characteristic impedance. So since the voltage value we have already derived, but for the dissipation loss line we have attained the line constant value, that is where gamma value is equal to alpha plus j beta, but attenuation will become 0 for the dissipation loss line. So the gamma value will be directly equal to j beta, and we know that the L value are going to consider that as a length of the line as x here. So what will be our voltage value? So V is equal to VR into ZR plus R naught by 2 ZR into e power j beta x. It is e power gamma. That gamma value is equal to j beta. The length you are going to see. So here, we are going to see what is beta into L. So beta into L we can call it as an electrical length. So this electrical length, what is the meaning of electrical length, or how we are going to define the electrical length? So the length of the transmission line expressed in terms of wavelength is called as the electrical length. That is, there are many lengths we can consider. For an example, that is 8 wavelength, quarter wavelength, and then half wavelength. How it can be represented? 8 wavelength means lambda by h. Quarter wavelength means lambda by 4. Half wavelength means we can call it lambda by 2. So this is called as an electrical length. So we are going to consider that here L as a x. So we will become the value become e power j beta into x. Similarly for I value already we have derived as I is equal to IR into ZR plus Z naught by 2 Z naught into e power gamma x minus ZR minus Z naught by ZR plus Z naught into e power minus gamma x. So we are going to substitute the values as for gamma as j beta, and we can get the I value here. So if you rearrange the values, we can finally get the V is equal to VR into cos beta x plus j into IR into R naught sin beta x. Similarly for I value, you can get IR by R naught into R naught cos beta x plus j ZR into sin beta x. So that is the two types of lines. That is, if the line is open circuited, what happens for the current value and voltage value, and if it is short circuited, and what will be the values of voltage and current. We know that if the line is open circuited, always we can say that open circuited, the current value is considered as a 0 value. So and what will be the voltage value? Whatever we are going to apply in the source, we can get it on the receiving end. Similarly, for a short circuited, we can say that the V value is 0. That is, VR is equal to 0. But current we will get the what we are sending in the input side. So here, if IR is 0, so you substitute that IR is equal to 0 in the voltage value. So here, what we value will get VR into cos beta x. Similarly, the current equation, if you substitute for IR is equal to 0, I is equal to j VR by R naught sin beta x. If the line is short circuited, we have said that VR is 0, so the voltage equation becomes j into IR into R naught sin beta x, and I is equal to IR into cos beta x.